as I've mentioned earlier, we won't have the time to do a really deep dive into the theory and into the fundamentals, but I still want to show you how easy it is to mess up an RSA implementation. And one way to do that is, for example, by choosing bad prime numbers. So there's an algorithm called Fermat Factorization that factorizes a number if its prime factors are too close to one another. Namely, if P and Q share half of their upper bits. So if you have a 512 bit prime, if 256 of the leading bits are the same in P and Q, then, for example, we can use Fermat factorization to factorize n and therefore recover phi of n, and then we can just calculate the private key. Now, this is a complete implementation of Fermat factorization, and as you can see, it's not very long, it's not very complicated, and it factorizes very efficiently. Now you might think, okay, how does it happen? How are those two prime numbers too close to one another? Well, especially in embedded systems, it's a big problem to generate randomness, to generate entropy. I'm going to talk about entropy later. So an implementer might be tempted to do something like this. He generates a prime number, say, okay, this is a truly random number and a prime number. And since we have used 512 bits of randomness here, which is really expensive, instead of just generating a new 512-bit prime number, just completely random, which is expensive, as I said, we could just continue. We could just count upwards from P and just take the next number that's a prime. For example, this function here, next prime, does exactly that. It takes P and just counts it upwards until it finds a new prime number, in this case Q. So now we have two prime numbers, they are large enough, and we can calculate n and phi of n. Well, as I said, we can use Fermat factorization. It factorizes this modulus in way under a second. So the prime numbers can't be too close to one another.